Thank you. Yeah, thanks everyone. Glad to be at Theory Lunch. So this is a bit of an experiment because I'm also experimenting with some new software for doing slides. So it can go well or it can go pretty wrong. We will see. Let's jump straight ahead. Okay, so this talk is inspired by a TV show. It's a show of the Mythbusters. And in this episode, we will be studying a particular myth with respect to AI, which is that decision trees are very interpretable machine learning models. So that's a myth we will be studying today, or a claim, let's say. So first, this work is based with a team of people in Chile, and now me at CMU. My spoiler, as opposed to the show, is already that decision trees are not going to be as interpretable as you might think. So expected questions to understand what's going on here is what is exactly the decision tree? What does it mean for a model to be interpretable? And why should we care about this in the first place? So let's see first what a decision tree is. So imagine you're Jeff and you're trying to organize theory lunch and seeing whether somebody can be scheduled for giving theory lunch next week, for example. So you might consider certain features of the problem to decide whether the date is available, whether it's a faculty or a student, whether that person already gave a talk this semester. Is there a lot of availability in the calendar? And is that a friend of Jeff? So with that in mind, Jeff can build a decision tree that will decide what to do. So you can see, for example, that if there's not a lot of availability, but you're one of his friends, well, maybe you can schedule it somehow. So then Bernardo, who's me, comes in. And the way you compute what the decision tree says is just by doing a path on the tree according to the features, right? So each internal node of the decision tree is sort of a question about a feature of the input. And depending on the answer, you will take either the left or the right path. And it's important to notice that no root to leaf path can ask for the same feature more than once. That means you cannot ask, for example, at this point, whether you're a theory faculty, because you already made that decision along the path until here, right? So if you allow that, you could allow for inconsistent paths, and that would jump in computational power to binary decision diagrams in general, which are much more powerful than decision trees. So now let's go to a hairy question. What does interpretable mean? Well, first, this is kind of an open problem. There's not a really definite answer yet. But here's a rough definition, mixing some things from the literature. Oh, sorry. I don't know what happened there. Some software quirks.
Can you move the Zoom?
What thing? Oh, I'm so sorry. Yes. Can I even make this disappear even? Like this. Oh, beautiful. Thank you. Thank you. So a mixture of definitions says that interpretability is about how easy it is for us humans to understand the decisions made by a model. So we can ask, well, how do we measure easiness? Which human, meaning that is it an expert in the subject or just a random user, for example? That will also matter. What does understand mean, right? That's also like the heavy lifting in the sentence. And finally, I guess, what does a decision mean, for example? That's kind of clear in the context of classification, but in regression context, for example, it's not exactly clear what a decision is. So in this talk, I'll be focusing on some particular forms of interpretability, local, post hoc, and in the context of binary classification. So local means that you're trying to understand what happens in a particular input as opposed to understanding the model as a whole. Post hoc just means that you're understanding a model after it's been trained. So it has already defined parameters. You're not trying to understand, for example, transformers for your exam next week, but this particular transformer with its particular set of weights. And the output is 0 or 1, right? That's binary classification. So let's talk about the mythos of model interpretability. So in 2016, Zach Lipton, who's now a professor here at CMU, published this paper as a short workshop paper, but it has actually had a large impact. That paper was challenging several assumptions in the field of interpretability, meaning things that people were saying about interpretability without really having much of a justification for them. So in the end of his abstract, it says, for example, that the questions the often made assertion that linear models, like a perceptron, are more interpretable than deep neural networks. And he does so in kind of a philosophical way. I guess you can think of my talk as a way to sort of ground this in theory. Nonetheless, even after years and citations, the same claims are part of the literature. So here's a compilation, for example. This is 3 years later in the DARPA interpretable AI. This very non-interpretable plot, if you map from here, it says that decision trees are interpretable models. They're high in explainability, for example. That's what DARPA thinks. This is again DARPA sort of comparing a decision tree with a neural network. This is MATLAB AI Lab, also saying that decision trees are very high in interpretability. Interpretable AI, which is a startup from 2018. And these are some slides, for example, even from a class here at CMU that's teaching about decision trees, and it says, for example, yeah, they have like high interpretability. So it's a claim often made by people who are in the business.
Can I ask a question?
Yes.
Interpretability, what does that mean? There's a document that a human can read and explain it to you, or what does it mean? You could ask a question of the model, say, why did you pick this instead of that?
Mm-hmm.
Can you explain that to me? Do you understand? Like,
Yeah.
an interactive one would be a different criterion than.
For sure, yes. So they're interactive proposals. They're also like sort of one message sort of protocols, meaning you only have the right, I guess, to ask one specific question. So there's various forms in practice that interpretability takes. There's various kind of questions, because when you say the question why, for example, you still need to be a bit more precise to get that to the computer. So we will see some examples of ways to formalize a why question. Why is this input classified that way? And then interpretability, I guess, or my take is about how easy it is to answer those questions. So in a model that's interpretable, you should be able to find a good answer to the question of why was your input classified that way. In a less interpretable model, that question will be either hard or unanswerable. So hopefully that gets a bit clearer, but we will see some particular like interpretability problems. So first, I guess, just why should we care about them? Well, the thing is, models are already being deployed affecting real people. And more importantly, they're being deployed in high-stake applications. So an example that's quite interesting, there's like entire papers just on these examples, but in the Compass system that was used for basically judging whether people will like commit crimes or misdemeanors, again, for example, given their past history. And then there were several analyses about how this model was racially biased in a sort of statistical sense. Another answer is because of a sort of philosophical belief of users that should have a right to explanations. This is even consecrated in the GDPR in Article 22. And if anyone of you has Twitter, for example, something quite interesting is that whenever you're receiving an ad, there's a button you can click that says, why am I seeing this ad? So you would expect that that's some sort of explanation of why Twitter thinks that ad is relevant to you. And I encourage you all to try it because the explanations they give are really bad. And it's part of the problem. They probably cannot do any better. But for example, I receive an ad for McDonald's. I click on that. Why? And it says, well, because you're a person between the ages of 18 and 85 who lives in the United States. But obviously, they do not deliver that ad to everyone filling those things, and therefore it's not really explaining what's going on. Okay, so what are we going to do now more concretely? We're going to study the harness of 3 interpretability problems over decision trees. We will consider our class of models as points of comparison. We will see some directions for tractability in practice and briefly discuss future and, I guess, ongoing work. So let's jump to the notation. A model in our context is simply a Boolean binary function. So from 0, 1, p to 0, 1. An instance is simply a vector in that space. And now we will say that a partial instance is allowed to take special value bottom that serves the role of an undefined component, meaning you don't know yet what value is going to be there yet. So with this, we can naturally define a subsumption relation between 2 instances that looks like this. So it's basically saying that the instance on the right fills in some missing or undefined information on the left. In this example, that's not the case because you fell at the beginning and you fell here. Moreover, whenever an instance is a partial instance is subsumed by another one, and the other one is an instance, meaning it has all the information, then we say that the instance is a completion of the partial instance. So in this case, for example, this one here is a completion of this one. It completes all the information that's potentially missing. And we will denote the set of completions of a partial instance Y as comp1. That's just some notation. Okay, so now abductive reasoning, it's one of the most popular kinds of explainability. So that means that we will be looking at subsets of the features that explain the classification. By explain the classification means that they are enough to fully determine what the classification is going to be. You know those features, you know what the answer is going to be. So those features sort of explain the answer. So we say that a partial instance is a sufficient reason for a classification C if it's a part of the instance and every possible way to complete it will give you the same classification. So you'll get the same verdict. This is also known in the literature as certificates, in particular in the world of complexity, and also as implicants in the world of Boolean logic. So let's do some examples. This is a picture of a cat. I binarized it, so it's part of my setting. This is a sufficient reason of a really bad model. So I train a model to basically just learn based on the number of white and dark pixels. So that model is saying, oh, this is a cat because it has a lot of dark pixels. So it's giving me that region in red, meaning, okay, if you take that region in red, then no matter what you do in the rest of the image, the answer will still be that I think that's a cat. And that's just because the red part already has enough black pixels to pass its threshold. Therefore, I know that that model is really bad. Why? Because I can change its verdict by simply modifying some of the black pixels to white, because I know that the model is sort of looking at them. And then I have this adversarial attack that's still a cat. It should be classified as a cat, and yet my classifier is wrong. If you train a good model, let's say I didn't code this myself, I just downloaded something from the internet that was good at this task, and it gives me basically that subset. So it's pretty much perfect in this particular cherry pick example, but it's telling me I think this is a cat because if you fix those pixels, then no matter what you do with the rest, I'll still think it's a cat. Now, these are some examples I compute with more realistic models. So these come from the MNIST dataset, and they're quite interesting. Here, for example, it's saying if you give those white pixels and those dark pixels, I'll always think that's a 1. And if you think about it, that makes sense. It's basically expecting some white pixels in the center that are surrounded by black pixels. You see some similar effect here. This is also by a decision tree, actually. So these examples are part of the of the paper. We compute them for decision trees with techniques I'll show later. Here, for example, it's a 9 that's correctly classified as not a 9. Sorry. So this is a decision tree that's trying to decide whether a digit is a 9 or not. So here it correctly states that it's not a 9. And you can see, based on this example, sort of about what the model is looking at for each of the particular digits.
So those are decision trees, and the white pixels are the ones.
So
The white and the red pixels are the ones it's using.
yes, those are the ones that are part of this sufficient reason. So the ones such that if you change everything else, it doesn't matter, the answer will still be the same. Yes.
So is this a minimal sufficient reason or even a minimum sufficient?
Yeah, good question. So I haven't say anything about that, but yes. So these are minimum. That one is minimal. Just a bit easier to compute. I also did some trickery in that one. I mean, it's true that it is an actual minimal sufficient reason, but yeah. Anyways.
But the 9, why didn't the same pixels show up on the last 2?
It's on the same.
Decision tree, right?
Yeah.
For 9.
Yeah, but it's on the same pixels. So here, for example, this is basically like looking at you having a black pixel here, sort of cutting off that possibility.
I see. So the path followed by the down the tree.
No, it's just like the features. So this is the three-dimensional representation of the vector of the binary vector. Right? So this is an input I passed, and I'm just highlighting which of the features are being looked at. But I think this will get clear in a second when I show some visualization of the decision tree. But this does not relate exactly to the path down the decision tree. Okay, so as I was being asked, you can define minimum sufficient reasons as a computational problem as trying to find a sufficient reason that has the least number of defined features. And if you think about it as a decision process, you'll be given an integer k sort of telling you how many features are you allowed in your explanation. So let's see first that sufficient reasons can be decided in polynomial time for decision trees. So how do you do that? Well, consider this instance. It does some path down the tree. So it does some path down the tree. And now consider this candidate sufficient reason. So I'm not sure yet if this is a sufficient reason, but I'm going to try to decide it. So it has some features, feature 8, feature 4, and feature 1. And the other ones are undefined. So what I can do as an algorithm is do a BFS from the root of the tree. And whenever I have an undefined feature, that means that I don't know which way of the tree I will go. So I'll expand both ways. But when the feature is part of the explanation, I just go where the feature is telling. So with that way, with that algorithm, you can see all the leaves of the tree that are reachable in a way that's compatible with the sufficient reason. And given that all of them have the same label, false, that means that all ways of completing that candidate sufficient reason will have the same classification. It turns out, however, that finding minimum sufficient reasons for decision trees is NP hard. This is something we showed in our NeurIPS 2020 paper. So let's start considering the set cover problem. You're giving a bunch of sets that are part of a universe, and you want to see if there's a subcollection of at most k sets that whose union equals the universe. So first, we will reduce this problem to finding dominating sets in directed acyclic graphs. So this problem is you just have a directed acyclic graph. The question is whether there's a subset of at most k vertices that dominates the graph, meaning that the set its neighborhood equals the vertex set. So here's how an instance of vertex cover looks like. that's a solution to vertex cover, right? If I take the union of those three, that gives me the universe. And I build this simple directed acyclic graph from there, adding one dummy node on the top. And my previous solution translates to a dominating set that just has k increased by 1, right? So that's just a very trivial reduction. Now let's see how to go from dominating set index to the minimum sufficient reason problem decision trees. So as the input, we have a directed acyclic graph. The first thing we'll do is to topo sort it. So computer topological ordering of the graph, it doesn't matter which one. Why am I doing this? So that's an interesting question. When you sort of think of the directed acyclic graph in a topological ordering, all your edges are going in the same direction. That's important because in decision trees, we said earlier that you cannot have, repeat questions in the same root to leaf path. So having this ordered property will allow us to avoid, to guarantee that we will avoid repetitions. So I will create based on this ordered DAG a decision tree. So you can see how the main sort of diagonal path is the reverse of this one. So 3, 6, 1, 3, 6, 1, and so on. And then the sort of subtree, for example, of 1 consists of 5, 4, and 2. And 5, 4, and 2 are the nodes that point to 1. So it's in neighbor. So if you look at this tree right here, you can think of it as an OR. That's computing the OR between 2, 4, and 5, right? So that's saying you need to select at least somebody from the set of neighbors of 1. And that's only in the case where you did not select 1. Because if you select 1, you don't need to select anything, it's in neighbor. So that should be making clear the connection between dominating DAG and sufficient reason. Let's see now some examples. So let's take the instance that has only ones. So that instance is classified as true just by my construction of the decision tree. And now consider a set, for example, 2, 4, 3. So my claim now is that this set is going to be a dominating set of the DAG if and only if its natural associate will be a sufficient reason in the tree. So when I consider set 2, 4, 3, these 3 nodes are part of my set, and these 2 nodes are in the out neighborhood of my set, whereas 5 is in neither. So this set is not dominating. And now what happens when you consider the partial instance that considers features 2, 4, and 3. So that means that the features number 1, 5, and 6, I'm leaving as free options. So in 1, for example, I'm not guaranteeing anything, neither in 6. So the problem here is that in 5, there's an option of going to false, which would mean that we're not a sufficient reason because we're not guaranteeing that the output will be true. And it's at 5 precisely because 5 is not dominating here, because I'm not covering any of its in neighborhood. Similarly, if we consider the set 1 and 5, then now vertex 2 is not dominated. And that will mean that when we do the sufficient reason algorithm, there will be at vertex 2 a reachable leaf with the false label. Finally, if we consider a set that is indeed dominating, like 2, 5, and 6, then when we run the sufficient reason procedure, all the leaves will be true, and therefore that is a sufficient reason. And the ordering part matters here because, as I said before, the guys who are going to be in the subtree from vertex 1 are the guys who point at vertex 1. So they must be behind him. Whereas the people who came before vertex 1 in this path are by construction vertices that come after. Therefore, it's impossible for there to be any sort of root to leaf repetition here. So for tractability, let me present some brief ideas. So we present some decision tree parameter that we call the split number, which is basically a measure of how disjoint the different subtrees are, meaning how many, it's some metric that captures whether a feature, for example, appears only on one tree or whether it appears on kind of all the subtrees. If that feature is low, you can actually solve the problem quite efficiently. And it's kind of a standard dynamic programming over a decomposition of the tree. We also determine a subclass of decision trees for which this problem is tractable. It's only a very theoretical result, but it's complete order binary decision diagrams with bounded width by K. And we also propose a practical set encoding that supports problems like the MNIST classification, so up to like 700 features and trees of up to 1,000 leaves efficiently. So those are the examples I showed before, and this is a lot of runtimes using a SAT encoding. So as you can see, it's in general in the order of magnitude of seconds. So what about other classes of models? A linear model, it's simply a pair, a vector and a threshold. And the way it works is basically you take your input X, you take the dot product with the weight vector, and you compare it with the threshold. If it's bigger, you say yes. If it's smaller, you say no.
Or move on.
Yeah.
I mean, why so simple? Let's awfully take away the like a negative result about interpretability of decision trees.
Yes.
So much to me. I mean, why is finding the minimum, certificate important component?
Mhm.
I mean, if this decision tree it's classified as one that follows the path. Seems like the best possible explanation.
Okay, yeah, so that's actually a great question. So when you say best, you agree that the root, like the number of features in the best route to leaf path is actually much larger than the minimum explanation. You can have a lot of redundancy in the path. In particular, yes. And also,
the minimum certificate is why is the minimum certificate do that's fine.
Okay, so yeah, that's a good question. So there's a couple of things here. One is that in practice, in industry, the sort of I think it was, I don't remember if it's average or mean, but of decision trees that are being used have like around 2,000 leaves and something like 300 or 400 depth, which means that in practice, looking manually at a root to path leaf can be quite large. So probably within the realm of doable, but it's large. When you find sufficient reasons, even for trees of that size, they tend to be much smaller. So on the order of magnitude of 10. So that's one thing, they're smaller. And as to why there are good explanations, well, they're telling you of some particular parts of the input that are in a precise sense enough to determine the outcome. I guess maybe I'm not sure of what other kind of explanation are you thinking, or
I feel that like it's like some weird coincidence that like reason the model of this instance, these 7 features happen to be the way that they are. Whereas it's more natural as a human to say like, well, I didn't output 1 because it follows.
Right, but the path is, I mean, the path is an explanation. The problem is that it's an explanation with redundancy, right? So a natural question is how to remove the redundancy. Yeah, or you can take the redundancy and yeah. Yeah, no, yeah. Yes.
Have you thought about the approximate version?
Yeah, so so there's some inapproximability that comes directly from the fact that the reduction from set cover or this dumb DAC thing, it's gap preserving, right? Because it's like a linear reduction. You also get like W2 hardness directly of that. And then I'm going to talk later about like sort of a probabilistic relaxation of this, in which you don't require all the completions of your explanation to get the same variable, but only a percentage of them.
So what's the personal result for upgrading?
Yeah, so for a neural net, for like general models, I guess it's MP to the PP hard to compute, and then cannot be approximated better than the dimension to the 1 minus epsilon, unless P equals MP. And then for decision tree, we have a conditional result that's like, yeah, under assumptions on contention between QP and MP. And that's also saying that you cannot basically approximate better than linearly. Yeah, but that the last one is unpublished.
So this is more philosophical about. You've done this like contrast. I can tell given whether it's efficient, but it's hard to find, right?
Yeah, to find the smallest one or a small one. Yeah.
But then like what? So like as the person clicking on why am I seeing this ad, if I see the reason, I can like tell it's a good reason, right? Whereas like Twitter, did a lot of work to find that reason, in a manner of speaking. So like you kind of put the burden of interpretability on like the person who has to find a sufficient reason rather than the person who has to try to interpret that reason.
Yeah, so that's a good point. Maybe I also forgot to say at the beginning that this is kind of like a position talk in some sense. So I believe you actually cannot do interpretability in a very meaningful way without looking at the model, meaning that there's no way for you to receive what Twitter gives you and have a good interpretation of why it's classified in a certain way, because you don't have sort of open box access to the model. And therefore, even though something might sound convincing to you, for example, my personal belief is that there's, like, for example, you cannot distinguish whether you as a particular individual are like a specific if else case, for example, the either in the code base, or it's like a result of some more general behavior of the model. So in general, I do believe that you need to be looking at the internals, like the weights or the structure it's the previous model. And usually, I guess like the way you think about this is, I don't know, if a bank, for example, is using a model to take your features and decide whether you would qualify for a loan, for example, the dream or my dream is that if the answer is no, let's say, for example, they're able to give you some parts of your feature, some like meaningfully defined explanation of why your features didn't.
In that sense, there's some regulations that ask for the explanation to be externable, meaning that exactly if you increment your income from this category to this other, then your prediction will change from 0 to 1.
Yeah.
I understand that in redundancy, that's not the case. Even though if I change 7 to 0 1, my path will always end up with certain decision.
Yeah, so there's like a, and there's also like a version of the problem I've studied, which is inspired by what you're saying, where you also consider how costly it is for you to change certain features. So if the bank is rejecting you, for example, and it's rejecting you because, I don't know, you live in a certain neighborhood, then switching neighborhoods might be much more expensive than, for example, I don't know, like getting a car, for example. And if either change is gonna change your classification, you might as well do the change. So there are sort of weighted variants of these problems. Yes. Oh, no. By tractability, I mean like that even though the problem is NP hard, there's some things that you can either do in practice or some sort of more specific theoretical cases that you can solve. So in particular trees with certain particular forms of structure, or in practice, you can do SAT solving, even though the problem is NP hard. So linear models, this problem becomes really easy to solve. It's just a matter of looking at the weights and sorting the weights, considering polarity, meaning considering whether the feature is 0, 1, but you know that the weights have like this very well-defined order of importance. On the other hand, if you consider neural networks, so for example, multi-layer perceptron with ReLU activations, we proved that this problem is sigma 2 complete. And it's kind of a cute reduction from a DNF minimization problem. So if somebody's interested, encouraged to look at that. So here's another relaxation. The previous definition might be too strict because it requires all the possible completions to have the same verdict. We can get much smaller explanations to remove even more redundancy by doing a probabilistic request. So we will say that a delta sufficient reason is one that guarantees that if you take a random completion of the instance, then it will have the desired verdict with probability at least delta. And just for the sake of the slides, I'm using the uniform distribution here. You can use more complex product distributions, and the same results will hold. So for example, consider a linear model of dimension 1000. So there's one feature that's very important. It has weight of 1000. All the rest have weight 1. Now consider the instance that's all ones, and the verdict of the model is clearly 1. So you take the dot product, it gives you over 1250. But any sufficient reason of probability 1 will need to have size at least 255. 251. We'll need to include the large feature and 250 of the other ones. Whereas in practice, you sort of want to say, okay, the important thing is the first feature. You have a 1 in the first feature, that's like pretty much saying it's super likely that you will get it unless you pretty much have 0 everywhere else. So that's how the probabilistic relaxation can lead to much smaller reasons. It was proved that the problem in full generalities and P should be P hard. And it was conjectured by Isa and others that this problem, both in the minimum and the minimal variant, minimal, I mean that you cannot remove any one feature and for it to still be the same, or NP hard for this. No, that's easy because counting like in a decision tree, counting the number of, yeah, you have like, that's a good question. Yeah, I'm working on that right now because then you can do, you cannot count, but you can sort of count, right? Yeah, if you smooth, for example, the value of delta, then you can do things. Yes, So for linear models, for example, you can approximate the count.
Yes, which way you settle?
Oh, sorry, maybe that's my English being wrong. I thought settling meant that you like prove the conjecture is as they stated it. So hard. The conjecture is that they're hard. We
wouldn't say.
Oh, okay.
I would prove.
Oh, I see. Sorry. Yes, we confirm. So something that's interesting is there's something strange that happens from the value 1 to like 0.99. So minimal sufficient reasons, when they're fully deterministic, they're easy to compute. Why? Because deciding sufficient reason for decision tree is easy to compute. And then to decide whether it's minimal, you try removing each possible feature and see if you're still a sufficient reason or not. But the reason why that doesn't happen in the probabilistic setting, it's because you lose some important monotonicity property. So this is an example where you lose the monotonicity property. So if you take the instance that has all ones, then the probability of acceptance is 1. And then if you remove features, the probability is 1/2. Except that if you remove everything, the probability gets slightly above 1/2 because of this little anomaly here. So that means that if I give you this instance and I tell you, oh, can you give me the smallest explanation that has a probability greater than, certainly greater than 1/2, for example, you will try to remove every individual feature, but you'll get 1/2. So you could say naively, oh no, whatever I tried to remove, I didn't get above 1/2. You actually need to remove everything to go above 1/2. So,
your explanation by deleting.
yeah, so you improve your explanation if your explanation is about having above a certain probability of acceptance. So you're like, in that particular sense, yes. In other words, that means that if you were concerned about, like, I don't know, let's say, for example, you assume that Twitter will use some randomness. So you're not fully concerned with something that would like guarantee that Twitter will recommend you McDonald's, but something that will make it likely. Then if somebody's able to prove you like, okay, for anyone in the world, it's like it has above the 50%, then you can be like, okay, I guess that's the reason why I was targeted. Just the pure nothing about me is enough. But that's because you're settling for a certain probability. So there's a bit of how working on this problem felt. We were debating for a year whether it was in classic polynomial time or NP hard. And it's finally NP hard. You cannot hope to compute a delta minimal sufficient reason for delta smaller than 1 unless P equals NP. The reduction here is really interesting and a bit tricky. So it starts from click, then it goes through a problem we had to make up. That's about the expected number of clauses you satisfy in a 2CNF formula. Then it goes to a problem about checking sort of a probabilistic form of contention in decision trees. And then you go from that to computing. I'm not going to do any of the reductions here, just some notes about it. So the first reduction is probably the most interesting. It's inspired by some work in the theory of valued CSPs. And then at the end, so just part of the message here is that when you're treating this as a decision problem, you're trying to check whether something is minimal or not. But it could be the case, and this is the case in some problems, that deciding is hard, but computing one minimal thing is easy because there's always, for example, by some theorem, a guarantee that there's always like a silly one that's minimal. So this is the case in things like Nash equilibriums, for example, where sometimes like saying that there's one is easy, but then it's like, oh, what about another one? And then you don't know how to do it. So you need to do some sort of trickery to avoid just being able to say that your problem is in the TFNP class. I'm going to skip this. It's the problem about satisfaction into CNF. Sorry. Oh, there's some slides, sorry, that I think didn't render. Let me. Yeah. Wish there was like a faster way to do this. Because I think there's some slides that did not render here. Or that rendered twice. Okay, I'll drop it. Okay, yeah, so my conclusions is that interpretability problems, or at least the ones that have been defined in literature in general, are hard even for decision trees. So given there were questions about this, I'm going to expand a bit more. So there's other interpretability problems you can consider. For example, you can think about counterfactual reasoning. So the idea in counterfactual explanations is what should you change in the instance so that the verdict changes. And there's some nice results between a duality between that counterfactual form of reasoning and the abductive form of reasoning of sufficient reasons, basically because if you have a sufficient reason that guarantees the output, then you, in order to change the verdict, you need to break it. So you need to at least change one of the features in all your disjoint sufficient reasons, and that will give you some sort of hitting set cover duality between the two. There's also work in computing Shapley values on decision trees. And it's actually a problem that in practice is hard. So that's another completely different form of reasoning that's much more numerical. It's also hard for decision trees. And at this point, one could think, well, this is just like some cherry-picked problems that turn out to be hard for decision trees. So how could we study this in more generality? And something we did was to define a logic, sort of a fragment of first-order logic in which you can define an arbitrarily large number of different interpretability queries and reason about models, and then study the complexity of that as a logic over models and how the complexity of evaluating sentences in that logic is also hard for decision trees. So that also yields another sets of interpretability problems that are hard for decision trees. There are paths towards tractability. Something I wanted to share is that part of the reason why I think that a lot of people think that decision trees is to interpret is because you look at small examples. When you look at small examples with like 30 nodes and depth 5, for example, it's easy to think that everything is easy to understand. But in my mind, that's similar to looking at a graph with 20 nodes, for example, and saying, oh, it's pretty easy to find clicks here. Because yeah, you can see it sort of like intuitively, but when it's like out of sort of what you can look in a screen, for example, and you have like 2000 nodes and depth 400, for example, then you really kind of need a computer to give you something. And then it's where the trouble starts. So part of what I think about the consequences of this is that there needs to be some work in rethinking what kind of explanations we believe that we can compute in practice, given that some of the most natural ones we cannot, or at least not superficiently. There's a lot of work in the field for what I call non-formal explanations, meaning that you, for example, can train, let's say, a neural network, and it will try to give you an explanation about another neural network. But that explanation does not come with a formal guarantee. Therefore, you don't have really formal semantics about what it means as an explanation. So it can be useful in practice in some cases for guiding things, but for example, I would be quite wary of giving that to users. And another potential consequence is that if even decision trees, which is like what one would expect to be the easiest case of all, is not as easy, then that might mean that in practice, rigorous, meaning that with formal mathematical guarantees, mechanistic interpretability might really be hard for kind of all models that achieve a certain accuracy in practice. So that's my, yeah, I think that's it.